Rather good morning to you all, and welcome to your sixth e-class. Today's lesson, we're going to look at causality and under linear time invariance platform, which will lead us to difference equations. Don't forget about their test, which is coming next week, Wednesday. It's gonna start. We're gonna start at 5:30 in the morning, and then we finish at around 7:30. The instruction used during the first test are applicable on that one as well. So let's look at today's work. Okay, you're familiar with the information right there on the first slide. No need to go through that. Okay, and we're just gonna get all the logistics right here. A causal system, well, as explained, it's only depend on current and future. It's not influenced by the past value. So right in brackets, round brackets, you don't expect any positive sign between the two values. So that's how it should look like. Now, here is a general equation for a difference equation used in causal system, which are LTI, which fall under LTI. So you can have a causal which is a non-LTI and which is not within our scope, but we'll be looking at the ones which are under LTI. If you look at that, this is the equation. Now you make y of n the subject of the formula, and you result to this. So it means this will be taken to the right-hand side. That's why they became, you see those minuses there. And you add to those values of x. But it's interesting here to find the output also depending on the output. So it's a form or some form of feedback. You've got the output, which depends on another output, or this. So in general, if we use the sigma notation, this is what you have. This being finite, it end on capital M and end on capital N. So this is your equation, different equation. We're gonna be applying that. It's important you remember that. And as in the first example here, 3.5, hoping that this 3.5 is the same numbering as in your textbook. Here you are given an equation, difference equation. So we have that y there as an output, which is also becoming an input, and x of n. Now, all you have to do if they ask you to identify the non-zero system, so where you have coefficients that were not multiplied to zero. So you take this equation and you compare with the general difference equation, you will find that these correlate with the coefficient of B0. Oh, no, sorry. Rather correlate with the coefficient of A1. And this one correlate with the coefficient of B0 there. Okay, now let's have a look. And maybe we need to fix. So there is a coefficient of xn, which is 1, and there's a coefficient of yn minus 1, which is 0.25. So we'll have to see that there minus a1 is really a coefficient of yn minus 1. So we go to that general equation. So that is a1 coefficient of y of n minus 1. And then from there, what about x of n? What was the coefficient of x of n, which is found there to be 1? There it is, x of n is b0, so that was b0, which we'll find to be a coefficient of x of n, which is 1. All right, so it's a comparison. You just take your equation, open up your difference equation, and compare the coefficients. We proceed with this. We're looking at the representation of a unit pulse response. Remember a unit pulse. We have to start from afresh with this pointer options here. We were using a highlighter, and color was blue. Right, go back to blue again. Now, a unit pulse function is like that, delta L. So now, what is the response to a linear invariance, time invariance system? So if you apply that, you will get the output to be h of n. Now, we have to check, we use an impulse response to represent any linear time invariant system. We use this notation. You feed in x of n, the unit pulse response of that is represented as h of n, and which will give you y of n. So bear in mind this, we'll use it to solve different problems that will be following. Here is another one of them. Now, they say a linear time invariance can be completely described by unit pulse response. So only on LTI, we remember the properties of LTI. The phase, the shifting is preserved. That's number one. And you can take the input values, apply them into the system. The output will be the same as if you have done the same to individual outputs. Right, so we covered that on our last lecture. That was e-learning lecture 5. So you can revert back to those slides there from revision. So now we are given an equation here. Now we want to see if we can represent that as an impulse response of delta n. So that will be 0.25 delta n plus 0.25 delta n minus 1. Oh, well, then which we're going to use the H notation as we go, but which is H of n. Determine the unit pulse response H of n. Okay, now how do we tackle that? Well, there it is, the unit pulse response. We use the H of n notation for the equation as it was. So that is 0.5 delta n, 0.25 delta n minus 1. So that is how you use the delta notation onto that. Right then, how do we represent this in a set form? So the only case where you have values is when n is equals to 0, when then the x of n is equals to 0, n minus 0, and when n is equals to 1, then you have the following values. There you have 0.25, because that is your coefficient, and that's your coefficient for 0, and you have zeros elsewhere. Okay, so now if we use the H notation, or how this x of n has been transformed to y of n, we say this. So we apply that general equation, which we looked there, to real terms. Okay, now, so the output y of n is given by h0 of xn, h1 of xn minus 1. All right, so then we finally used our H notation. There are many examples regarding this. Please go through all of them. More likely, when you get this in the test, it will be one of those examples, similar or related, but you can't get it exactly as it is. Now, there's another one. If you have another equation, you are given the difference equation, it's important to note there that in this instance, unlike the previous one, if you look at the previous one, we didn't have y at the input. There was no y anywhere here. But if you look at this, it has got y, n. So it's important to note that, which is added to x of n. So as it was in a difference equation, but we're looking for n values greater than 0 and y of minus. So this is your initial value at y of minus 1. Determine the unit pulse response, and you sketch the block diagram. It's more or less similar to what you did, but in applying it to a different equation. Right. Now, firstly, they say they want to replace x of n with delta n. Now, so x of n became delta n. That's fine. But what about y of n? Y, remember, is the transfer by delta. So you use the H notation where there was y. That is the difference. We didn't have of this example to the one we did earlier. In this case, we had y of n minus 1. So y is an output after transfer of x of n, where we use this for impulse response, letter H. Now, we use first 3 values to find the numbers. If we come here in this equation, we substitute 0 for n, and then we solve. This is what we're gonna get. 0.25, and then from there, times 0, okay? And then remember, y of, let's look at this, y of minus 1 was 0. So that's where we get 0 there. So that's y of -1 is 0, and which times 0.25. So the only thing which exists, it will be x of n at 1, which is, that will be equals to 1. The difference equation also already tell us this is just 1, 1 multiplied by delta. So you add 1, you have 1. On the next lot now, we are not talking about y of -1. It's not an initial condition anymore. You move away from that and you're looking at 0 and then h of 0 and then you add. So that 0.25 will count, multiplied by 1. And then when we look at that delta at 1, it became 0. So you have 0.5. Now, you can carry on with this, and then the next one will be 0.25. It's interesting to note that when you take this divided by that, you get 0.25. This divided by that, you get 0.25. So it's like you were multiplying by 0.25 throughout. So if you multiply by 0.25 throughout, is you are raising it to n. It's like you're gonna be raising it to n and you use it as a unit rep function. So a unit, not unit rep, I like calling unit rep, unit step. Remember a unit step function is something which goes like that. From 0, you got ones all the way. But now we've got coefficients which are dropped. So it's like you are taking 0.25 and multiply by n, which is ultimately like taking 0.25 and multiply by 0.25 all the way. So which from that you start having a diminishing output. So if we have to draw this, we have a unit step. Well, it was unity, but it start its value going down because of this exponent. So it's important to note that how they change from delta n to unit step function. So there it was delta, which was supposed to occur only on the origin. Okay, so now we apply that onto the formula, and then our formula will be that. Now, if we have to evaluate the values of y0, y1, y2, and we have to go and substitute the value of values of n, these are the values which we will find out. And you can use the convolution method to do the same, right? So, ladies and gents, it's important for you to go and evaluate these examples and make sure that you understand. Like I said, as explained, there are more and more examples to this. I can sit here, spend about 2 hours, 3 hours, the whole day explaining this, but it's within you to visualize this and analyze it in your own way to understand, and then be able to reproduce this if you happen to be asked. And the study there for chapter 3, it concludes by bounded in and bounded out stability. Please also look at that section, and that will close the chapter. As for your test, I can randomly ask you the work for chapters 1, not too much of it. chapters too, but not theory, of course. If I have to ask you something from chapter 1 and chapter 2, it will be more of giving a sequence, a discrete time sequence, and like as you represent it, the representation, or putting it in a set form, but relating to the work of chapter 1 and chapter 2. I can't say give the diagram of a circuit block. So, well, you don't even have to go and study, go and do the work of chapter 1 and chapter 2 per se. It's something which form the basis of chapter 3, which I may ask to the application of what you learn in chapter 1 and 2 as in the context of chapter 3. So it's like saying the question which I ask about chapter 3 may require you to go back and look at your work in chapter 1 and 2. I hope I'm clear with it. So it's not that you should go and redo chapter 1 and chapter 2. It's like for you to understand some other question, you might have to revert back to chapter 1 and 2. So what will be the core there? It will be chapter 3. It's a long chapter. You see, we will spend weeks on that. So there you're going to have types of sequences, which you must be able to sketch, describe, and illustrations. So it must be put this and how to illustrate. And same as the systems. I ask you to give the output equation for various systems represented as block diagrams. So if you have x of n here, for instance, and is being transformed by that system, what will be y of n? How do you write y of n for that? So those you should know. And LTI, you have to show systems, whether they are LTI or not. So you might be given an equation and say, is this time variant, time invariant? Is this linear or not linear? As described in your previous lecture, e-learning 5. And today's work as well, where we looked at the difference equation, how you apply using them to evaluate inputs. So how do you use give y in terms of unit parts? So those are the kind of things which you're going to be asked mainly in the test. I hope I'm clear with that. Then just again as a reminder, your test will be written next week, Wednesday. So that will be the 21st. 21st of April. That's when you write the test, 21st of April. And we start at 5:30 in the morning. 5:30 in the morning. So prepare well. And good luck. Don't forget to visit all your slides. So the slides which you got after the test. And again, I'm going to put your practical on your U-Link at my earliest convenience and send you a notice to your WhatsApp. As soon as the notice is there, attend to it. You will have to submit that on that other week of the 28th of April. With that, I'll say to you, good luck, have a nice weekend, stay safe.